In this video, we will revisit the emergency department model that we looked at in Module 9 and use OptQuest and the KN tool to solve the resource allocation problem. So recall in the model that we did before, we were modeling an emergency department of a hospital, and we have 4 different patient classes, and they follow different routes through the system. So the trauma patients go to the trauma room and then to treatment and leave, and the routine, moderate, and severe initially go through a registration and an exam. After the exam, the routine patients leave, and the moderate and severe go through treatment and they leave. And we decided that what we were interested in was the total cost of a configuration, and the configuration was defined as a particular number of exam, treatment, trauma rooms plus a given number of nurses and doctors. We're also penalizing total patient waiting hours, so we can offset the cost, because clearly if we had all of the cost for the rooms, then our solution, or the minimum cost solution, would be simply to have no resources. But we want to make sure that we treat the patients, and so what we initially did was we just set the we penalized the cost function for patient waiting hours. So let's take a look at the model that we ended up with at the end of Module 9. So you can see that we have our patient types here, routine, severe, moderate, and urgent, and associated with each patient type we have a priority, so that the highest priority goes to the urgent patients, followed by severe, moderate, and routine. We had the patient mix for arrivals, and we also have a tally statistic associated so that we could track the waiting time for each patient type. And so patients would arrive and follow the respective sequences through the registration, exam, trauma rooms, and treatment rooms. We have the reference properties for the doctor, nurses, and the 3 room capacities that we want to experiment with. We also have the secondary resources for the doctors and nurses, and we define lists to allow us to choose from the doctors or the nurses and give relative priority. So in the doctor list, in the doctor-nurse list, we give priority to the doctor and then the nurse, and in the nurse-doctor list, we give priority to the nurse and then the doctor. And so when we had in the different rooms, we wanted to allocate priorities differently for the secondary resources. And for the user statistics, if we go to our definitions, we mentioned that we have the 4 tally statistics for waiting time for each patient type. We also track the number of patients in the system, and then we have an output statistic for the total cost, and this is where we allocated the cost for the individual rooms plus the doctors and nurses, and then of course we penalized the total waiting time also. And so we used add-on processes so that we could track the waiting time of patients, and then when patients left on the normal exit, where we accumulated the total waiting time so that we could use that in the cost function. We also designed an experiment so that we have our controls representing our doctor, nurse, and room capacities, and our responses were the waiting times, the average waiting times by patient type, along with our cost, and then our average number of patients in the system and the final number of patients in the system, so that we could establish whether our system was stable or not. And so that was the model that we designed in Module 9. And one thing I want to do before we do the optimization is fix one minor oversight that we had in this model. And to show that, we need to look at the individual patient types and how they move through the system. And so we see that the trauma patients, the moderate and severe patients, both come to the treatment room from a previous location. So the trauma patients come from trauma to treatment, the moderate and severe patients come from exam to the treatment room. And so when patients get to the treatment room, they've been at a previous location. And so tracking the waiting time in our original model, we used this temp entity state. So what we did was, when the patient arrived at the treatment room, we marked the current time, then we seized the doctor or nurse resource, and then we assigned the interval between the before the seize to they received the doctor resource, and we added that to the total waiting time. And so that's how we accounted for the fact that we needed to add the waiting time for the treatment room. Of course, what this doesn't capture, and the oversight part, is this method doesn't capture the time that patients spend waiting for the treatment room itself. So when a patient leaves the exam room or the trauma room and they're waiting in the queue for the treatment room, so if there's not a treatment room available, this method doesn't capture that waiting time. And so what can possibly happen in our experimentation is that we miss waiting time if we have an insufficient number of treatment rooms. So to fix this problem, what we need to do is the marking of the temp state for the model entity needs to happen when the patient leaves the trauma room and when the patient leaves the exam room, rather than when they actually arrive to the treatment room. So I'm going to take the assignment and remove it, and then I'm just going to paste that same assignment into the after processing of the trauma room, and then paste another copy in the after processing of the exam room. So now what happens is, when the patient leaves the exam room, we release the doctor or nurse resource, and now we mark this temp attribute of the entity. Similarly, when they leave the trauma room, we release the two resources that we had, and we mark this temp attribute. Then when the patients, if they're severe, moderate, or urgent, they then are routed to the treatment room. And so we then seize, once they receive the treatment room, we seize the doctor or nurse resources. And at this point, we now can mark, or we can tabulate that additional waiting time. And so the modification that we did in the model captures that waiting time for the actual treatment room itself. So now that we've made an update to the model, I'm going to go back to our experiment, and before we do the optimization, I'm simply going to reset and rerun the experiment to make sure that the updates that we did actually take effect. And so what we're going to do is we're going to let the same experiment with the 10 scenarios run, and we will then just compare the results that we get in the updated model with the results that we got in the model from the end of Module 9. Okay, so our experiment's finished, so let's have a look at these values, and let me try to fix the screen here. And what I'd like to be able to do is bring in the values that we got from the end of the model from the end of Module 9. So if I can get these both on the screen here, we can see that the routine hours don't change in any of our scenarios. So we start out with 0.373978, 0.373978, and then scenario 10, 0.129085, 0.129085. However, for the moderate, severe, and urgent patients, our scenarios, many of our scenarios, we have higher values for our waiting time in our new model than we do from the model from the end of Module 9. And this is exactly what we would expect, because we've modified the model to capture that additional waiting time. And so if we did further experimentation, and this is something you should try on your own, we would see more severe differences if we reduce the capacity of the treatment. So in the models that we looked at, we have all of the treatment room capacities at 6. If we reduce that treatment room capacity, we would see a more dramatic difference between these two models, because our updated module captures that additional waiting time. Similarly, the costs are higher in our updated model to account for the fact that we have more entities waiting. So now we're comfortable with our model, and we feel that it adequately captures the situation, and so now we can move on to solving the underlying optimization problem. The first thing that we're going to do with our optimization is we will define patient satisfaction as the proportion of patients who spend no more than 30 minutes waiting. In the previous module, in the assignment portion, we just focused on routine patients. This time we're going to focus on all patients. So what we'd like to know is what are the proportion of patients who go through our system who spend less than this threshold value, which we will initially set at least as 30 minutes. And so in our model, in order to implement that, what we need to do is let me go back to our facility view, is when a patient exits, we need to decide whether or not they spent less than 30 minutes, and we will use two different model states. We'll increment those states respectively whether they did or didn't spend more than 30 minutes. Then we'll create an output statistic to compute the ratio, to compute the proportion that spent less than 30 minutes. So I'm going to go into our model definitions states, and I'm going to define two new states. I'm going to define an integer state for, and call this num satisfied, where we will track the number of satisfied patients. Similarly, I'll have another integer state called num unsatisfied. So we have now defined two model states, num satisfied, num unsatisfied, and we go to the process associated with normal exit. So here, where we incremented our total waiting, at this point we know how long an entity waited. It's recorded in the model entity state waiting time, and so we'll simply add a decide module here, and the condition will be model entity waiting time less than or equal to 0.5. Oops, less than or equal to 0.5. And so that's the condition. Did the entity wait less than or equal to 1/2 hour? If so, I'm going to increment my num satisfied. Otherwise, I'm going to increment, there's our increment. Otherwise, I'm going to increment our unsatisfied. So num unsatisfied equals +1. So we have num satisfied equals num satisfied +1, and num unsatisfied equals num unsatisfied +1. So now when an entity leaves, when a patient leaves, we will increment the corresponding value, determine whether or not they were satisfied. And so the next thing we need to do is define our output statistic. So I'll go back to definitions, elements, and I want to create an output statistic, and we're going to call this satisfied. Or actually, let's name it satisfaction. So this will be the satisfaction percentage. And what we want to record in our output statistic is the num satisfied divided by num satisfied plus num unsatisfied. Nominally, this is the expression that we want. However, we'll have a slight problem at time 0 before we have any patients that go through the system, the denominator value will be 0, and Simio will potentially give us an error. So we're going to use a math max function here to just sort of trick this value, at least in the initial stages. So this is going to be, sorry about that, right here in our denominator, math max of our two values. And so our first value is our nominal value, and we'll just have 1 here. And so when we look at our expression now, what we've simply done is we've now made this the maximum of our num satisfied plus unsatisfied and 1. So when these values are both 0, the denominator will be 1, and when the first value becomes greater than 0, then this value won't matter. And so now we have an output statistic for satisfaction, and we'll go back to our experiment, the same experiment that we did before, and let's just add a response for satisfaction. So satisfaction And of course, the value that we want is the value of our satisfaction output statistic. And so we'll add that there. And then let's reset our experiment and let it rerun and come back and check our satisfaction values. Okay, so now the experiment has completed and we can look at our satisfaction values, and you can see as we have fewer resources, our satisfaction level is quite low. So when we don't have sufficient nurse or doctor capacity, then we don't have acceptable satisfaction levels. And as we add resources, we can see that we are increasing our satisfaction levels, which makes perfect sense. So in the case where we have the maximum number of resources, 5 doctors, 6 exams, 6 treatment, 2 trauma, and 10 nurses, we see that we are satisfying almost every patient in terms of that 30-minute threshold value. So in the next video, we will continue with the optimization to try or to use, and we'll use OpQuest to determine what an optimal allocation of resources is in order to minimize the total cost function.